I like to think of data scientists as black boxes, right? You put data in, and an API comes out. Or you put data in, and a visualization comes out. And I'll talk about what sort of tools we've built at all different parts of this diagram and how we end up supporting data scientists through this. So first of all, we need to get data to our little black box data scientists. Like I mentioned, engineering is a different department than algorithms. And so this presents a really unique challenge in getting data and getting data in a format that data scientists want. So while we don't write ETL for our data scientists, we expect data scientists to own their ETL end to end. We do capture data from engineering and get the source tables that all ETL derives from where they came from. So there's sort of a history here in how we've captured data. Originally, we would get nightly snapshots of the transactional databases that are used to support our engineering teams. So you can imagine immediately that one problem with this is that the fastest that we could keep up to date with new customers is nightly. So there's at least one day before we can start styling new customers if we stay with a system where we only have nightly snapshots of these transactional databases. We have moved to a system for some types of data where we're capturing the events as they come in. So important events for us are things like the survey. When a customer fills out a style survey and they tell us what it is they're looking for, what kind of fit they like, what kind of style of clothes they like, we then create an event in the survey service, and we can more quickly respond to that and begin to create recommendations for that particular person. So historically, we were doing snapshots, and we've now moved to an event-driven system. So that's great. The black box now has some data to work with, and I assume that what they're doing is a bunch of math, probably. But it's pretty important to think about how it is that these data scientists have actually take the math that they're thinking of, test it out, and try it out pretty quickly. There's three important systems that we end up using to support data scientists in building these models as quickly as possible. First of all, we have a system called Pearl, which allows us to build all different types of images, and in particular, Docker images. So as I mentioned before, we have data scientists doing all different types of modeling and using all different types of languages. People use R, people use Python, people use all different types of packages in them, and we don't want to restrict what it is that they're building. And so we have a system that allows them to build Docker images really easily, and then define what it means to run a job inside of that Docker image. And so that is called Flotilla. Flotilla is essentially for us just a wrapper around ECS, Elastic Container Service from Amazon, which allows people to say, I'm running a Python job. This is the GitHub repo that this Python job lives in, and this is the entry point into it. This is the command I need you to run. It expects these arguments. And from there, we can do exactly what you would hope we would do, which is schedule it, right? Data scientists aren't just building one-off models. I mean, of course, sometimes they are. But once they start putting things into production, it's a pipeline, right? It needs to start happening regularly. And they need to get alerted if that doesn't work. And so we recently put Airflow into production. We've had a long history of different schedulers. Initially, we were using Jenkins, which is extremely reliable but limited, right? Jenkins, for us, didn't allow us to have a fan-out and fan-in pattern needed for a lot of these pipelines. We had some ways around this. People built little tools. And we've now moved to Airflow, which is in production, and we have almost phased out our legacy systems. So that's a new deadline that's coming up at the end of the year, which data scientists are always really excited when you change the platform on them. You're like, OK, I need you to stop building new models and use this new piece of platform. And they're thrilled. They can't wait. Good, I'm glad some of you liked that joke, because man, data scientists do not like it when you change their platform. They have jobs to do, right? And their job is to build models. It's to deliver better things for their customers, and their customers are their business partners usually. And I think fundamentally that's one of the biggest challenges in any data department is that you do need to evolve your platform. You need to change it. You need to keep it up to date. But trying to do that as seamlessly as possible for data scientists ends up being very important because they have jobs that they want to do too. So we have ways of defining these jobs on AWS for them, and they've been really quite popular. Flotilla in particular is extremely self-service. I think one of the things that's made it particularly easy to use is that on our data platform team, we have a UI engineer. And he has built UIs for different systems that we use that make it extremely easy for that to be self-service from data scientists. I think most back-end engineers, which are most data platform engineers, they're very inclined to say, here's a CLI, you can read the documentation, they'll figure it out. And I think as soon as you actually give a UI to people, people become a lot more comfortable with searching for what it is they're looking for and immediately figuring out what a certain system does. And I would say most people eventually move to using the CLI after they become comfortable with it. But when you first join a company and you're like, how do I define a job? How do I schedule it? What does this look like? Being able to go to a URL and see a list of all of the already defined jobs is extremely beneficial and useful. And so I think that really keeps our data scientists happy, is having a UI engineer that helps us present a clear, uniform platform to our data scientists. This is an example of what Flotilla actually looks like. Flotilla has been open sourced, so if you're interested, you can go look at Flotilla OS, Flotilla-OS, on GitHub. And it comes with this UI as soon as you start it. So that's great. You know, we can create a job, we can schedule it. It runs regularly, it'll alert us. What's really, really hard about analysis and model building is not the pipelining of it. I think many companies have the tooling to do that reasonably well. What's really hard is to make it reproducible, make it accurate, and make it collaborative. So having good analysis reviews, being able to rerun some sort of model building process and get the same model out. Working in Silicon Valley, my favorite question to ask after a few drinks with other data engineer people is, so what's the most embarrassing part of your platform? Or like, what's your most embarrassing data engineering story? And people will share some really fascinating things. The number of times that I've heard that there's important models people use that they can't rebuild. It's impossible. The data's moved along, the code has moved along. They're not really sure how it came about, but it works, so they're just kind of making sure that they have multiple copies of that model somewhere. It's really, really high. So that is a direction that we're really trying to move in building this platform for analysis, is how do we make it easier to make this reproducible? How do we which is very related to data lineage. Where did this data come from, or where did this model come from? Of course, when people are building these pipelines, they're really trying to get at building some sort of artifact, right? So maybe the end of an ETL is a table that other people use. We have this one system that this falls in the horizontal category. The team that builds this is in the horizontal team. What they do is we have an application that's called Style Shuffle. You can get it on the mobile app, or you can get it on Facebook, and we show you clothing items, and you tell us whether you like them or not. And this is actually extremely valuable to us. This Style Shuffle application allows us to build better models for recommendations than we have otherwise. So one of the issues that we have in building recommendation models is that if we only used information about what people bought, we would have very, very sparse data set. So if you were to compare it to something like Movie Lens, the sort of classic recommendation data set, it's about 100 times as sparse. And that's incredibly difficult to build models off of. we build them, and they improve our accuracy of shipping people things that they like. But if we can get more data that is more dense than what people buy, the better. And so this style shuffle data ends up being extremely useful for us. And people that aren't even customers yet can play it. And from that data, we've built recommendation systems and embeddings, and like embeddings into style space, into a latent style space of what people seem to like, that allow us to solve cold start problems and have much better early predictions. No. And the artifact that they produce is actually an embedding of all current customers, as well as a transformation matrix that can take new customers that we have no information about into our latent style space and help us solve our cold start problem. Other people, the artifacts that they're producing are maybe serialized models that they're going to deploy into production. So there's, again, a big variety in how people train models and a big variety in what artifacts people are actually creating and sharing with the business, what their end goal is. One of these, of course, is dashboards or visualizations. So we have a BI tool. We use Looker. And then that is extremely useful to us. We don't want data scientists constantly putting out graphs that are relatively easy to make if you're using a BI tool. And that's one of the reasons that the analytics engineering team that I mentioned earlier is so useful and fascinating. So when I said, OK, we have data scientists. We don't pre-process things for them. We sort of grab data and let them do what they will. I think you should have like alarm bells going off in your head about having so many different data scientists building all of these different definitions of things. Because owning a single thing end to end, where you're focused on styling recommendations, or you're focused on merchandising, doesn't necessarily mean that you're building reliable ETL, repeatable ETL, shared definitions of certain metrics that are probably important. You don't know if those are necessarily the same. And so having an analytics engineering team that can build the right type of shape of a data warehouse, and in our case, that's a dimensionally modeled data warehouse, ends up being extremely useful because then data scientists can have a bit of shared data that is well prepared, well cleaned, and we can point a BI tool at it, and that takes care of a large number of sort of simple requests coming from the business about how this metric is doing over time or how that thing is working. But outside of that, we actually also want to make sure that we're building really useful integrations with the business. So we have a fair number of custom tools that we have built for making merchandising purchasing easier, for example. We have people that previously their workflows were thousands of spreadsheets over the course of a quarter, where we now have simplified it by building a UI for them. And so we have a team inside of the data platform that specializes in partnering with data scientists and building UIs. So this is an example of not necessarily building an API that engineering is calling, but building a tool that we present to other parts of the business. And we have pieces of this that are meant for deployment, and meaning that if you're on our VPN, and if you're on our VPN and you have the right permissions, you can see certain applications that we've built internally. And we have some very nice functionality around shiny dashboards too, which I very much like. Oh boy. Oh, good. Okay. Now, when most people think about building machine learning models and that sort of style of data science, they're thinking of services. So we need some way of taking data, training a model, and then actually applying that code and presenting an API. So this gets used in all parts of the data science organization, but particularly in styling. Let's think of that as an example. We have engineering building this application, And this application is used by stylists. They sit down, and they get a new order that they need to fill. And we want to be able to present an API that says what the most likely, like the top 100 most likely items this person might buy. So for data scientists to own this end-to-end, there's some things that make this a little bit easier for us to build abstractions around so data scientists can just sort of build this thing. In many, many cases, in cases where you need really, really low latency, for example, in model application, or you need real-time responses to new data coming in, you might not be able to let data scientists own building these services and having them be supported end-to-end by data scientists. In our case, our latency requirements aren't that high, or low, depending on how you look at it. And so what we end up doing is we have a system that allows us to define a Docker image that most people run in, and they might install a few other libraries that are needed. It allows them to define tables that exist in our data warehouse that they want copies of in local memory on the machine that's serving their model, and to define a function that takes in some sort of data. So we're using Python 3, which is really fascinating because that allows us to have type signatures in the function that is getting applied to data coming in. And from that, we automatically create an API. So let's say this takes in a function that's called, let's say that we define a function called apply. And the signature of this function is a client ID, which is an int. That would then create an API which accepts a post request with an int value being passed in, and would return whatever you say it's going to return. Frequently, people are returning data frames, which we wrap up in a special way, and we wrap up in a special way that ends up being JSON serializable, and return it to the calling API. So some combination of Python and Docker, a little bit of black magic, allows us to give data scientists a way to say, I need this data. This is how I apply my function to new data coming in. And then we even create a swaggerized API docs that our engineering counterparts can look at and see, oh yes, this is exactly what this particular function expects in terms of input, and this is what I can expect in output from it. But of course, we don't want to just have a single API. We want to experiment, right? So A/B testing ends up being extremely important to us. We have a unified A/B testing platform, which again, extremely self-service. People define how they want their experiments bucketed, how they want clients allocated. And this A/B testing service has a few components. There's the live allocation component, meaning engineering will say, hey, I want recommendations of clothing to the allocation service. The allocation service will say, here is the URL that you should call to get recommendations for clothing. And behind the scenes, it's doing allocations into an experiment where we might be testing a new recommendation system version. And we then record what happens. We record what happened with that order, if people bought things or not. And there's a self-service dashboard that the data scientists that are running live experiments can look at. The product managers and people in engineering that are concerned about that particular part of the product can also look at. One of the major benefits of having a centralized A/B testing platform is that we can agree on what sort of metrics we want to compare and measure and optimize for, and what those definitions of metrics look like, and make sure those metrics are calculated uniformly across all A/B tests. People can't argue that, oh, really, I was trying to optimize this other metric. So it's important for us in building this system where we can serve different types of models that we're not only sort of blindly thinking that the system exists and is doing well, we also integrate with PagerDuty and automatically create PagerDuty notifications. We have good logging, and it's easy to find the logs from this service. And of course, we present Swagger APIs, and just sort of think about the engineering that needs to go in around these services, the data scientists don't have to do that all manually and custom. So a good question that I've tried to answer along this is what has been working well? And so I think that one thing that works really well about what we've set up is that people can really own things end to end. We really, really, really do encourage that, and I think that actually happens. I think another thing that works particularly well is data platform engineers take the time to understand what data scientists are doing and what is hard or easy for them. And I think there's obviously challenges. One of those challenges is related to that analytics engineering team. I think before there was an analytics engineering team, it was really hard for a new data scientist to come on board and understand what is happening across all of the teams, or what sort of data exists generally, or who created it. And so pretty quickly, in this extremely independent, autonomous, ownership-oriented department, we realized that what we need to do is track what people are doing and have a software-based idea of ownership. And so we have this really great system. Again, having our own UI engineers is really handy, where we are able to tag and label different systems. So you can imagine that a team or a data scientist might own a variety of jobs, that might own certain tables, they might own certain services. And without this consistent view of saying, like, this is the team name, show me all tables, jobs, services that they own, it would be kind of a mess. Trying to do any type of migration would be really hard. Trying to understand why some job is taking up all of the resources on our Spark cluster, you don't even know who to talk to. So we learned pretty quickly, as an early challenge, that we need to be able to track people and to track what our data scientists are doing and have a concept of ownership. And one of the things that's really beneficial about us doing that consistently is that we can then present it in a UI to them. So we have a sort of universal dashboard where data scientists log on and they see, these are my jobs, they all were successful last night, except maybe this one which failed, and then they can click through and see what failed there. Or they can look at different services that are up or different A/B tests that they're running. So that's really what I have to say. Thank you.
Thank you so much. So we have time for several questions. Whoa, 16 upvotes. How to hire full-stack data science people? Do they exist in nature?
Yes. So I think that one of the things that happens is that you build them, right? You need to understand that for each particular role, what kind of skills you're looking for. And usually in data science, there's certain types of mathematical inclinations that people need. So maybe they need to know a lot about, integer and linear programming. Or maybe they're more statistics-y than machine learning oriented. And you hire that along with some amount of interest and motivation to learn more. And when that is paired with autonomy and ownership and the type of people that excel in autonomy and ownership, those people will go and learn more skills. And so you need to be willing to create full-stack data scientists. Not everyone's going to come perfectly prepared. But if they're the type of person that feels really, really motivated by being able to have a problem that's theirs and solve it, and you've hired people on the engineering side who are really happy to teach people and sort of up-level in skills, then you can create full-stack data scientists. So I think it does exist. It's hard to hire for, but if you provide autonomy and ownership and being able to define your own problems, you become a more appealing place to work. And I think that's another part of what works well about the Stitch Fix model is that data scientists want to work there because we have our own department. You get to work with a lot of other smart data scientists. You get to own your problem end to end and be creative in solving it. And that is really appealing and has allowed us to hire well.
Thank you. Do you plan to replace human stylists with AI stylists?
We always think of the marriage of human intelligence and tools to make it easier and faster to do people's jobs, right? I think the personalization and the sense of like style and taste is really important. And so one thing that I haven't mentioned about, well, I think maybe I did mention this. One thing that people really like about Stitch Fix is you open up the box and there's a letter with a little note from your stylist. And that human touch is really important. I think it adds to the customer experience, and it's not something that if we created with a robot would have the same effect, I don't think. Maybe if AI got kind of perfect, but I think something that's really interesting and challenging in a lot of data science roles is that if you're creating tools to do something in a business, there's usually already a human that does it. And so you need to make sure that you're not threatening that human by completely replacing them. And I think with stylists, we never think that we're going to get rid of stylists. We think that stylists are an important part of what we create. But we want to make it easier, faster, more fun, more creative for them, so they don't have to go spend a lot of time searching through things and having their system be hard to use. Instead, we want them to be enabled and feel like they get to do the more creative human part of their job, which they tend to enjoy more anyway.
So that's like yes, but later part. Okay. What happens to clothes which are not bought by anyone?
Ooh, that's a good question.
They become very sad.
Yeah. Well, so you can imagine that we have a warehouse that's full of clothing, and we set it out to people, and some of it gets bought, and then other stuff comes back. And if we'd never got rid of clothes, our warehouse would be full of clothes that people don't want, right? And then the pool of clothing that we're sampling from, meaning the pool of clothing that we're sending out to people, is clothes that people don't want. That wouldn't make any sense at all. So what we end up doing is we clearance some of the items, meaning we don't sell it, we remove it from the pool. And that goes to a few different places. We're doing experiments with different things. We have an employee store where we can go buy things for very, very, very cheap. We've also just started experimenting with an outlet store in this SF Bay area.
Nice. So Flotilla sounds like a CI product. For example, drew it from a somewhat different angle. What made you create your own solution instead of adapting something that already exists?
So Flotilla isn't quite continuous integration. It's maybe related to continuous deployment. Flotilla is actually just a relatively simple wrapper around the Elastic Container Service. And the vision, so my team is the one that works with Airflow, Flotilla, and I think seeing CI as innately linked or really tightly linked is a good sort of vision. What I would like to see is that we move to a world where data scientists are doing something a little closer to Heroku for data science, where they say, here's my repo, this is the Docker image I want to run in, this is the definition of how and when I want it to run, and we just sort of magically take care of that in a CI/CD kind of way.
Cool. Thank you so much. Let's do one last question. Can you give us an example of a model built by data scientists and how that helped both customers and the business?
Sure. Let's talk about the items that we don't sell, right? So we have models of what items we need a clearance from our warehouses. So when you think about clothing items, there's the SKU, which is at an item level. So for a particular style and a particular size, you have a SKU. For certain style variants, that's generally what we want to clearance. And so we have a data scientist that is responsible just for building models of what style variants we need a clearance from our warehouse. And that helps the business by making sure that we're not taking up space in our warehouse with things that aren't selling well. And it helps our customers by making sure that they're not getting items that they don't like.
Thank you so much. Round of applause.
Okay, thank you.